actually seen some infinite sequences before. Specifically in grade 11, you would have looked at arithmetic sequences and geometric sequences. Do you guys remember those? A little bit? I'm getting flashbacks. You're getting some flashbacks? That's good. Hopefully good flashbacks. Okay, so an arithmetic sequence would have looked something like this, for example. I don't know, 5, 8, 11, 14, okay? Okay, so this is your A value, it's your first term, and then you have a common difference, right? So in this case, what is the common difference? 3, right, okay? So that's an arithmetic. Okay, and you also, an arithmetic sequence is basically like an adding sequence, right? You're adding a specific amount to each term. You also looked at geometric sequences. So you may have looked at something like this. I don't know, let's start with 7, 21, 63, 189. Okay. So what's the pattern here? Multiplying by 3. Yeah. So a geometric sequence is a multiplying pattern. Right? And we start with our first term, which is A, and then we multiply by something called R, which is the common ratio. Okay, so these are two types of sequences, but there are other types of sequences as well. You don't just have to have this type of sequence. Okay, so for example, we have one here, 1 1/4, 1/9, 1/16. What would the next one be? Yep. Okay, so I'm going to tell you something. Neither of these are geometric or arithmetic. These are different types of sequences. But can you figure out the pattern? What would the next number in this sequence be? 1/25. Correct. This is 1/25. And the next one? Yes. Okay. In general, we're looking at 1/n squared. Does that make sense? Okay, so if we're looking at the limit of this sequence, if this is an infinite sequence, right? The limit as n approaches infinity of this sequence, 1/n squared, what is that? We looked at limits at infinity earlier last week. Yeah, it is 0, yeah. Because 1 divided by an incredibly large number is 0, right? And you can see that these numbers are getting smaller and smaller and smaller and smaller and smaller. Okay? What about this sequence? So we've got 1, 1, 2, 3, 5. Does anyone know what the next number would be? Yeah. It is 8, yes. This is Fibonacci sequence, yes. Yeah, this is Fibonacci sequence. Okay, so this is 13, and then 21. So what's the rule? How do you get the next term? What's that? Exactly, you add the previous two numbers. So the rule for this sequence is T1 equals 1, T2 equals 1, my bad. And then Tn equals Tn minus 1 plus Tn minus 2. Okay, so you've got to define the first two terms, and then every term after that you can define by adding the previous two. Okay, now what's the limit of this sequence? The limit as n approaches infinity of Tn. What do you think? Yeah. It is infinity, yeah. Because this is just going to get larger and larger and larger and larger and larger. Exactly. This is infinity. Yeah. Okay, now to figure out some of these, we're going to use some of the things we learned last week around limits at infinity, okay, which we've already seen. So suppose Tn equals n cubed plus 4n squared plus 2 over n cubed minus 3. What is the limit as n approaches infinity of Tn? So how would you start this one? If we're looking at the limit of Tn, yeah. Yeah. Yeah, divide by the largest power of n in the denominator, okay? So if we look at that, right, if we're looking at the limit as n approaches infinity of this guy, this is like a rational expression, then we can divide by the largest power of n in the numerator and denominator. So that's n cubed over n cubed plus 4n squared over n cubed plus 2 over n cubed over n cubed over n cubed minus 3 over n cubed. Okay, and then if we simplify, limit as n approaches infinity, this is going to become 1 plus 4 over n plus 2 over n cubed over 1 minus 3 over n cubed. And when you plug in infinity in this denominator, what's 4 over infinity? 0. And 2 over infinity cubed? 0. Yeah, and this one is also 0. So this becomes, and if you wanted to, you could add an extra line where you have 4 over infinity, 2 over infinity cubed. I'm going to skip that piece, okay? So we're going to get 1 plus 0 plus 0 over 1 minus 0, which is just 1. Okay, now for this next one, I want you to try and imagine if we were to graph this. Let's say we were to graph y equals 2 over 5 to the x. What type of function is this, and what does it look like? Yes, it's an exponential function. Okay, so exponential functions, if we don't think of any transformations, look like that. Okay, with no transformations. This is our y-intercept, right? What does the value of b tell us, the base? Do you guys remember? No? Okay. Let me just think. It might be helpful to, just because this kind of thing comes up a lot, let's pause for a second and just look at that. And that. Okay, and I want to take a look at this because we no longer have access to graphing technology. Okay, so we have to have other skills available to us. And so if you don't know what to do, I want to sort of model for you that you actually do have tools that are available to you. Okay, so you can always kind of use table of values, that sort of thing, to figure out what's going on here. So what I'm going to do is I'm going to come up with some x values, and then I'm going to look at both of these, 2 to the x and a half to the x. Okay, so let's say I look at -2, -1, 0, 1, and 2. Okay, so if x is -2, what's 2 to the -2? It's not 4. It's 1 over 4, because it's 1 over 2 squared, right? So this is 1 over 2 squared, which is 1 over 4. Okay, if x is -1, what's 2 to the -1? 1 over 2, yeah. If x is 0, 2 to the 0. 1, yeah. If x is 1, 2 to the 1 is 2, and 2 squared is 4. Okay? All right, let's look at the next one. So, a half to the -2. Yeah, it's 4, because I can flip the fraction, right, the reciprocal, and then this sign changes. So it becomes 2 over 1 squared, which is 4. Okay, this becomes a half to the -1, which is 2. Okay, this is 1. Half to the 0 is 1. A half to the 1 is a half. And a half squared is a quarter. Okay, so if I look at what these would look like graphically, okay, maybe I'll do them in different colors. So let's say I'll do this one in red. Okay, so this is y equals 2 to the x. So when x is -2, y is a quarter, so that's about here. Then when x is -1, y is a half. There's 1. There's 2. And there's a quarter. So this guy looks like this. Okay, and along here, we actually get, as x approaches -infinity, we get a horizontal asymptote. Does this look familiar? A little bit? Okay, good. I know it's been a little while. Okay, let's switch colors. So for the other guy, we'll do green. Okay, so when y equals a half to the x, when x is -2, y is at 4, so that's here. And when x is -1, y is 2. When x is 0, y is 1 rather. When x is 1, y is a half. And when x is 2, y is a quarter. So this guy, basically we get a reflection. Oh my gosh, this is terrible. Okay. In the y-axis. There we go. Okay, so this is what these exponential functions look like, essentially, right? And for both of these, the a value, which is the number that we essentially multiply the power by, is 1. It's 1 times 2 to the x, 1 times a half to the x, which is why our y-intercept is 1. Okay, so the y-intercept for both of these is 1. Okay, and then we get these graphs where one side is going to be a horizontal asymptote, the other side is going to go up to infinity. But it's like, which side is which, right? So how do we tell? The way that we tell is the base greater than 1 or between 0 and 1? Okay, if it's greater than 1, if we keep multiplying by something bigger than 1, we're going to get bigger and bigger and bigger and bigger and bigger and bigger. And so it's going to look like the red one. Okay, if we multiply by something smaller than 1, like a half, we're going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller every time we do it. And so it's going to look like the green one. Okay, and so why is that relevant? Well, if we're looking at this guy, every time n increases by 1, we multiply by 2/5 again and again and again and again and again. Okay? Every time we multiply by 2/5, are we going to get bigger or smaller? Smaller. So as n goes to infinity, what is this going to equal? 0. Yeah. This guy graphically, let's switch back to black. Okay? Looks like this. Right? And these exponential functions will all take one of two shapes. It'll either go this way with the horizontal asymptote going towards the right, or they'll go the other way, where the horizontal asymptote goes towards the left. And it all depends on the value of b. Okay? Is it greater than 1? Or is it between 0 and 1? Okay, so this equals 0. Okay, now if we look at this one, the limit as n approaches infinity of 2 to the negative n, well, 2 to the negative n, if we write that using positive exponents, what would that be? Yeah, it'd be 1 over 2 to the n. And in fact, we could write that again as the limit as n approaches infinity as 1/2 to the n. Because 1 to the n is always just 1. Okay, well, what's this one going to equal? 0 again, yeah. Because again, we keep multiplying by 1/2 over and over and over and over and over again. Every time we do that, we're going to get smaller and smaller and smaller and smaller and smaller until eventually we get down to basically 0. So as n approaches infinity, this limit's going to be 0. Okay, and in fact, this was the green graph that we drew, right? This is this guy. Okay, good so far? Yeah? Okay. All right, let's look at a couple more. Okay, so let's look at this guy. Limit as n approaches infinity here. So 4 plus 1 over the square root of n. Okay, so the limit as n approaches infinity of 4 plus 1 over the square root of n. Well, the only part that has an n in it is this second part. So 1 over the square root of infinity. What's that? 0, yeah. So this is going to be 4 plus 0, which is Okay. This one. Limit as n approaches infinity of 7 to the n. Well, that also looks like an exponential function. Which one does that one look like? Is that going to go like this or like this? Which one? The first one, yeah. So it's not this one, it's this one. Okay, so as n approaches infinity, what is this limit going to be? Infinity, yeah. Exactly. Okay, now let's take a look at this. Let's compare these limits. So the limit as n approaches infinity of 3 to the n, and the limit as n approaches infinity of -3 to the n. And to do that, what I'd like to do is let's just write out a few terms. Okay, these are infinite sequences, but let's just write out a few terms. So if n is 1, if we're just looking at Tn equals 3 to the n, okay, and here Tn equals -3 to the n, okay. If n is 1, this would be 3 to the 1, which is 3. If n is 2, this would be 3 squared, which is 9. 3 cubed, 27. 3 to the 4, 81, okay, and so on and so forth. Okay, so what's the limit for this infinite series, or sequence rather? Infinity, yeah. Okay, if we look at this guy, T1, -3 to the 1, what's that? -3, yeah. -3 squared, +9, yeah. -3 cubed, 27, sorry, -27. Okay, -3 to the 4, 81, yeah. Okay, so here we have a problem because the limit's not really approaching infinity, right? Because it really depends on whether n is even or odd. If n is even, the limit approaches infinity. If n is odd, the limit approaches -infinity, okay? So if n is even, the limit as n approaches infinity of Tn is infinity. If n is odd, the limit as n approaches infinity of Tn is -infinity. What does that mean about the limit of this infinite sequence? Doesn't exist, yeah. So the limit, therefore, the limit as n approaches infinity of -3 to the n does not exist. Okay, now let's look at these two on the other hand. Okay, so here we've got the limit as n approaches infinity of 1/3 to the n versus the limit as n approaches infinity of -1/3 to the n. Okay, so if we just look at some terms here, okay, so if we look at T1, T2, T3, etc., we're going to get 1/3, and then 1/3 squared would be 1/9. Yes? Okay, 1/27, 1/81. If I wanted to do the next one, that would be 1/243. Okay, and so if I were to sort of draw this on a number line, here's 0, here's 1/3. Okay, so there's a third. Here's a 1/9. Then here's 1/27. Okay, here's 1/81, and then maybe right here is 1/243. Okay, what's the limit? 0, yeah, right? We're getting closer and closer and closer to 0. So limit as n approaches infinity of 1/3 to the n is 0. Okay, so that's that guy. Now let's compare that to this one, where we have Tn equals -1/3 to the n. Okay, so if n is 1, what's T1? -1/3. And T2, 1/9. T3, -1/27. T4, yep, 1/81. T5, 1/240, no, -1/243, right? Because I'm -1/3 to the 5 is 5 negative, so -1/243. Okay, so if I draw a number line here, now I've got positives and negatives, so I've got to draw a 0 in the middle. So here's 0, and maybe just to orient myself, here's -1/3, here's +1/3. Okay, so I start here, and then here's a 9th, and then here's -1/27, and then here's 1/81, and then here is -1/243. Okay, so what's going on here? Yeah. Yeah, I'm getting closer to 0. I keep hopping over 0 every time, but I still keep getting closer to 0, right? So I go here, 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 here. Okay, I'm approaching 0 from either side. Okay, so although I have positive and negative values in the sequence, the limit is still 0. Okay, so in general, when we have these sort of exponential expressions, they won't all be exponential functions, because when you have an exponential function, that base value must be positive. Okay? But when you have an exponential sort of expression, you're looking for the infinite, the limit of the infinite sequence. Okay? Okay, well, it's going to be infinity if r is greater than 1. Because if you multiply by something bigger than 1, you're going to get bigger and bigger and bigger and bigger and bigger and bigger. Right? That's like when we had 7 to the n. It's going to be 0 if we have one of these two examples, right? Well, this is sort of less than 1. What we have to have here is we have to have the magnitude less than 1. Do you guys know what I mean by magnitude? Like the number part. So how do we write that mathematically? It's the absolute value. Okay? Those were like those last two examples. And then if r is less than 1, like -2 or -3, what would the limit be? Or less than -1, I should say. Like what we saw here. This guy, that was less than 1. What happened there? It didn't exist, yeah, right? Because depending on whether n was even or odd, one of them approached infinity, the other one approached -infinity. Okay. Another way you could write this guy, by the way, is or that. Okay? All right, does anyone have any questions? Okay, so I'm going to stop there for today.